So, hello everyone who's watching this on YouTube. So, I just get started in 5-10 minutes. I'm just waiting for a few people to join the session in person. So, I guess I'll get started in 10 minutes. If no one joins the session in person, I'll start discussing the problems anyways. So it seems no one has joined the session in person yet. So anyways, I'll get started for the YouTube audience. So hello everyone, just to reintroduce myself, I'm Lakshya Saggi, the problem solving TA for the Monday 6 to 8 p.m. sessions for the NPTEL Games and Information course. I believe this will be our ninth session, and in this session we'll be discussing about uh, make strategies in extensive form games. Basically, these topics were discussed in this week's lecture. So everything including uh, Kuhn's theorem and what are behavioral strategies and yeah, what are normal form strategies in extensive form games. So yeah. So again, this week's lectures were much more theoretical in nature. So I thought it's maybe a good idea that in the first half of the session, we'll try to discuss more about the main theory or main points which were discussed, main key takeaways from this week's lectures. So these can act as some sort of quick revision notes for you guys also in the future. And after covering up the main concepts which were after like going through the main ideas which were discussed in this week's lecture, we'll discuss some of the problems. So yeah. So maybe we'll just get started. I'll just share my screen and we can get started with the discussion. So yeah. Uh, so I guess my screen should be visible to everyone now. Yeah. This is the week 9 again, like I said. So first we have some kind of like I just took out the key takeaways, the main notes from the lecture, and wrote them in form like just copy pasted these key notes into this into these slides and or into this document. And yeah, after that we have some questions related to these kinds of uh, related to these also. So let's just get started with discussing the uh, theory first. So till previous week, what we discussed was what are pure strategies in a extensive form game, and we also discussed what kind of equilibriums are present in extensive form games like multi-state feedback games, threat equilibriums, and a lot of things were covered. But as we had discussed previously also, when we were discussing like when we were not discussing extensive form games but rather simultaneous games, that uh, it need not always be true that that an equilibrium exists in a pure strategy, but like always like an equilibrium will exist in mixed strategies. So a mixed strategy equilibrium will always exist. And what does mixed strategy mean? Mixed strategy means that we form a probability distribution over the set of pure strategies and choose one of the pure strategies at random from according to that probability distribution. So yeah, so randomization plays a key role, as you must have noticed till this course, that randomization plays a key role in like all of these equilibrium and stuff. So now we'll be discussing about these mixed strategies or essentially randomization in a dynamic game. So how do we define what do we mean by randomizing in a dynamic game? So again, in simultaneous game, it was easy to discuss randomization because every player was playing simultaneously. So we just said that every player, according to a probability distribution, picks every pure strategy according to that probability distribution. So every player has its own probability distribution over pure strategies and picks a strategy according to that distribution. But in discussing randomization in a dynamic game, like there can be multiple definitions of randomization. Like one definition can be in terms of mixed strategies, another can be in terms of behavioral strategies. And what do we mean by these? So one definition can again be the same as what we discussed in simultaneous games, that form a probability space, form a probability distribution over the pure strategies for a player in the dynamic game. Note that even though players' actions might come at later times, but a player strategy is defined. A player strategy can be defined at the start itself, right? So strategy, what is a strategy? A player strategy is just function from like every information set of the player to the action it will take at that information set. So there are many pure strategies for a player, and yeah, you can pick one of those strategies at random using some kind of probability distribution. And this is just say this is what we call a mixed strategy. This is what we call a mixed strategy in simultaneous games also. But another form of randomization can occur in, like, we can think of randomization in another sense in a dynamic game where we are not randomizing at the start itself. We are like, here what we are doing is in this mixed strategy, we are randomizing at the start itself. That we say that our first step is randomization, and we'll randomly choose a pure strategy. But another concept can be, okay, maybe I don't, and using that randomization, I define all of my future steps. In a mixed strategy, I define all of my future steps at the start only. Though those steps are chosen at random, but everything is defined at the start itself, before the actions even begin. But another thing which I can do is maybe I don't define everything at the start, but I do randomization as I go along. Like so there can be you can think of a notion of time in a dynamic game, or like different turns of a player. So a player can think, okay, maybe in my first turn I'll do something randomly, and then when my second turn when my second turn arrives, then again I'll choose something randomly at that point. So I'll not fix what I've chosen at my second turn at the start itself, but as my turn comes, I'll choose it. And this is what you call a behavioral strategy, where you are essentially making an action at random at each information set as you arrive at that set. So you are not choosing a strategy at the start itself, but as you arrive at the information set, you will be choosing one of the strategies at random. So, for example, you can. So one example here was like, so this is an extensive form game where player one is playing two times. So player one plays in the. So this was example also given in the lecture itself, that consider this form of an extensive form game where, like, player one has kind of two turns. So player one plays first L1 or R1. If L plays L1, the game finishes. If he plays R1, then player two plays something. And now P1's both nodes are in the same information set. And this means that P1 can't distinguish between what L2 and R2 has played. And now again has to play something from L1 or R1. So consider this as this is a perfectly valid extensive form game. And now what we'll and why we are discussing this example. So one might think, okay, that we have defined these two definitions: what is a mixed strategy, what's a behavioral strategy. But one might think that these two things are actually the same. Like, even though their definitions are different, but what if these two things are actually equivalent? So then from this example, actually, you can show that these things are actually not the same. Like, these are inherently different things. Like, a mixed strategy and a behavioral strategy inherently are two different things. So for example, here you can think that like, what will be the set of. So first of all, just let's consider what about the mixed strategy. So what kind of a mixed strategy will be there for player one? So let's consider player one strategies. So how did we define mixed strategy? We said that we'll choose a pure strategy at random. So let's form a set of pure strategies. So what will be the set of pure strategies for player one? So player one's pure strategies will be playing, like, there are two information sets for player one, this set initially and this set. And in both the sets, the only possible actions are L1 or R1. So one strategy will be L1 L1. So both information set play L1. L1 R1 will mean first play L1 and then play R1. Similarly, R1 L1 and R1 R1. So note that you might get confused that, okay, if we are playing L1, then player one second turn is anyways not coming. So why are we defining this second L1 also? But like, just this is how we define pure strategies, that even though we might not reach that information set, but we always define an action for every possible information set. So this is just in the definition of pure strategies. And it does not make really much of a difference anyways, as you can observe. So the set of pure strategies for P1 will be L1 L1, L1 R1, R1 L1, and R1 R1. And now a mixed strategy will actually be a probability distribution. So we'll be picking one of these four strategies at random. So so the set of mixed strategies for P1 will be lying in a space of R to the 4, because L1 L1 can be played with probability P1. This can be played with probability P2, P3, and P4. And the sum of these four probabilities should be equal to 1. So we kind of have four variables for mixed strategies, P1, P2, P3, P4, and one constraint that some of the variables should be equal to 1. So essentially, the mixed strategies for P1 can be characterized by actually three parameters, which are basically probabilities P1, P2, and P3. So probability of playing L1, L1, probability of playing L1, R1, and probability of playing R1, L1. Because R1, R1 will actually anyways be equal to like 1 minus some of these three. So set of mixed strategies is characterized by three parameters. Whereas if you think about the set of behavioral strategies for P1, so behavioral strategy means that at every information set, you're choosing an action at random. So, so this is the first information set, and here you can choose two actions, which is like playing L1 probability alpha and R1 probability 1 minus alpha. And in the second information set, again you have, so you can play L1 or R1 with probability beta and 1 minus beta respectively. And this is the only randomization which occurs in the behavioral strategy. So as you can see that the behavioral strategy is actually characterized by just two parameters, whereas mixed strategy was characterized by three parameters. So inherently, mixed strategies and behavioral strategies are uh, not the same, right? But again, like even though they are not the same, but again, a question arises that can we still simulate one thing by the other? So like, can we still form a behavioral strategy which is actually the same as a mixed strategy? And similarly, can we form a mixed strategy which is same as a behavioral strategy? And what I mean by the same is something what we'll define by an equivalence of strategies. I'll just mute myself for a minute, guys. I'll just come back in 2 minutes. So sorry for that, guys. So now we have to define and so first of all, if we want to say that these strategies, whether they are the same or whether they can be simulated, we need to have an actual definition of what we mean by simulation, right? And this definition is what is called equivalence of strategies. So on a high level, on a very high intuitive level, uh, like a mixed strategy is said to be equivalent to a behavioral strategy, or like vice versa. If the mixed strategy can be uh, actually implemented, like given any mixed strategy, you can form a behavioral strategy which is equivalent to it. And what do we mean by equivalence? By equivalence, we mean that in the game tree which we have, uh, probability of reaching any vertex. So every vertex in this game tree will have some probability of reaching, right? Corresponding to, like if we are playing a behavioral strategy or a mixed strategy, any randomization, we will have in this game tree some kind of a probability of every node, like of reaching every node. Like this node is reached with probability alpha. Let's say if we are considering like, let's say behavioral strategies for now. So this node is reachable with probability alpha. This node is reachable, P2 is reachable with probability 1 minus alpha. And then what is the probability of being this node being reachable? It is like probability 1 minus alpha times probability of P2 playing L2 at this point, right? So every node has some probability of reaching. So we say that two strategies are actually equivalent if this probability distribution of reachability over all the nodes is actually the same for both the strategies. So yeah, so this is the kind of high level intuition, and this is the actual definition also. A mixed strategy sigma I and a behavioral strategy bi are equivalent if for every mixed/behavioral strategy and every vertex x in the game tree, probability of reaching x under the assumption under if the person is playing sigma I should be equal to probability of reaching x if the player is playing bi. And this mu minus I is just like saying that every player apart from the player I is actually playing the same set of strategies. Like the other players can play some behavioral or mixed strategies or anything, but if like the for all other the if for all players other than I the strategy remains the same, then we say that if every other player is playing the same thing, then if I play sigma I or if I play bi, it does not matter in my game tree. Like probability of reaching every node will be the same. And if this kind of a thing occurs, then we say that the mixed and behavioral strategies are actually equivalent. So note that this is a kind of very strong requirement that what we want is so given a mixed strategy, we want a behavioral strategy which is equivalent to it. What we'll have to show is we'll have to first see what's the probability of reaching some node under the mixed strategy, and then we'll have to form an equivalent behavioral strategy. So this is kind of like okay, one can define anything, but then like does this definition even help us in any manner? Like does equivalent strategies actually exist also for does a behavioral strategy exist? Does an equivalent behavioral strategy exist for every mixed strategy and vice versa? This is what we'll discuss later, but this is the notion of equivalence of strategies. And it's easy to see that just another fact that if a mixed strategy is equivalent to a behavioral strategy, then uh, like ji refers to the payoff of player I. So if all other players are playing the same thing, then the payoff for player I if the player plays the mixed strategy and the payoff for the player I if the player plays the behavioral strategy will actually be the same if all other players are playing the same thing. And this is not too hard to see. This is just a relaxation of this concept that like every node in the game tree has the same. Let's say sigma I and bi are equivalent strategies. So this means that every node in the tree has the same probability of reaching under sigma I as well as bi. So this means that these payoff nodes also have the same probabilities of reaching under sigma I and bi. And so the expected payoff is just like probability of reaching some node times payoff of that node and summed over all the payoff nodes. So that probability also remains the same. And that's why payoff underplaying sigma and payoff underplaying bi will actually be equal if sigma is equivalent to bi. So I hope this kind of argument makes sense. And if it does, then like again, like I said, that we have defined something like equivalence of strategies, but is it even useful for us? Like, can we say that for every mixed strategy, does there even exist a behavioral strategy and whatnot? So actually, what we can show is, so this was discussed in the lectures also, that in general, mixed strategies and behavioral strategies are not equal. So, so like, so there exist mixed strategies for which there will exist no behavioral strategy. And similarly, there exist behavioral strategies for which there exists no equivalent mixed strategy. And these examples were discussed in the lectures also. So I'll be discussing one of the examples. So like they can like yeah, I'll be discussing a behavioral strategy in a game tree which won't have any equivalent mixed strategy. Similarly, another example in the lecture was given of like a mixed strategy which has no equivalent behavioral strategy. So there was an example given in the lectures about a mixed strategy having no equivalent behavioral strategy. And like, so both sides, actually you can show that both sides are like there exist strategies in both sides which are not equivalent. So there exists a mixed strategy which is not equivalent to a behavioral strategy, and there exists games in which like there exists a behavioral strategy which is not equivalent to any mixed strategy. Okay, like you can actually show both sides. Like you can actually have examples for both sides. So I'll discuss just one of the examples. So this example was given the lectures about existence of a behavioral strategy which has no equivalent mixed strategy. So like suppose this is the game tree, and maybe like let's just suppose like this P1 is the start node, and like uh, so at first stage also P1 is playing, and the second step also P1 is the player itself, and both of these nodes are in the same information set. Okay, so what does this mean? This means that P1, if P1 plays L, again P1 arrives at the same information set. So P1 is kind of forgetful, and P1 does not even remember what it has played. Like P1 can't distinguish between these two nodes. So P1 can't distinguish between whether it has played L or it has not played L, right? So what are the set of pure strategies for P1? So pure strategies for P1 are just L and R, because like pure strategies is just like the set of actions corresponding to each information set of the player. So there is just one information set for P1, and the only two outgoing actions uh, out of this information set are L and R. So P1 can just play L or R. So these are the only two possible pure strategies for P1. Okay. So now note that in any pure strategy, like if P1 plays L or if P1 plays R, if in any of the pure strategy, P1 cannot reach this node O2. And why is this the case? Because suppose P1 plays the pure strategy L. So P1 always plays L. This means that P1 is always playing L. So at first step, P1 plays L. And in this step, again, P1 can only play L. Right. So why does a strategy like playing L first and R second does not exist for P1? Because there is no notion of, so why does this kind of strategy not exist, that P1 plays L and then P1 plays R? Like this kind of pure strategy does not exist because P1 is forgetful. Like P1 cannot distinguish between these two nodes. So actually there are no two layers to P1. Like P1 cannot say that I played LR. Like P1 cannot distinguish whether it has played L or it has not played L. So either like, so these are not actually two stages for P1. This is just one stage. So P1 can only play L or R. Or in simplification, like you can just think that this is the same information set. So like P1 cannot distinguish between these two nodes. So these two nodes can be considered the same. And so there are only two outgoing actions from this high level set, which are just L and R. Right? So there are only two possible pure strategies, which are L and R. And so if P1 chooses the pure strategy L, then P1 just goes to play L, and then again it plays L. So it goes to O1, and P1 plays R, then goes to O3. So there is no way for P1 to reach to O2. So no pure strategy of P1 leads it to O2. And since a mixed strategy, so this is where the definition of mixed strategy kicks in. So in mixed strategy, what we do is we first find the pure strategies and then choose one of the strategies at random, right? So one of these L and R strategies, say there are just two strategies for P1. So one of these will be chosen at random. So according to some distribution. But note that if either in any of these two strategies, like if we choose L or if R is chosen, in any of these two strategies, P1 won't reach O2, as we have already discussed. So for any mixed strategy, P1 will not be able to reach O2. Like the game will not end at O2 ever. Okay. So that's why probability of reaching O2 under any mixed strategy is 0. So the game will never end at O2 in a mixed strategy if the player P1 plays a mixed strategy. But note that in a behavioral strategy, actually, there will exist a behavioral strategy where P1 will be able to reach O2. Like the game can end at O2. So consider the behavioral strategy of P1 playing L with probability half and R with probability half. So what does this mean? So at first stage, like initially P1 plays L with probability half or R with probability half. So with probability half, P1 comes here. And again, P1 has to play something. And so with probability half, P1 can play R at this stage. So half times half, which is 1 by with probability 1 by 4, P1 actually reaches O2 in this behavioral strategy. Right? So note that so there exists a behavioral strategy where there is a non-zero probability of game ending at O2, but there exists no mixed strategy where the game can end at O2. So here we have found a behavioral strategy, this behavioral strategy, which will have no equivalent mixed strategy, right? And that's why you can say that in general, mixed strategies and behavioral strategies are not equivalent. And okay, just again, just reminding you guys that the key idea here is like why does why does mixed strategy not exist but pure behavioral strategy exists is because in a mixed strategy the set of pure strategies is chosen at the start before P1 even starts playing. The set of pure strategies can be defined, and so before even P1 even started playing, P1 has chosen one of the strategies at random. P1 has chosen one of the strategies at random even before it has started playing. So it has chosen like one of the strategies LNR even before it has started playing. But in a behavioral strategy, uh, P1 is actually not fixing what it's going to play at the start. It's playing, uh, it's doing randomization at every step. Like at its every turn, it's doing some kind of a randomization. It's not doing the randomization just at the start, but it's doing randomization at every step. So at first step, P1 does randomization and tosses a coin and goes to L or R. And again, even though these are the same information sets, but P1 has to again take some action, right, at this step. And so previously, what we had said was like in a mixed strategy, like if the pure strategy L was chosen, then P1 will have to play L and then L. But in this behavioral strategy, if P1 is at this node, P1 will toss a coin again. And now it can go to one of L and R. So essentially, P1 is doing two coin tosses. You can think of it as like this, that P1 is doing two coin tosses in a behavioral strategy here, but it's doing just one coin toss in a mixed strategy. And that's essentially why the difference comes that in one case, O2 becomes reachable, but in other case, O2 does not become reachable. So this is the kind of high level idea. In a mixed strategy, we fix everything at the start, whereas in a behavioral strategy, we do it per turn basis. Like I'll do randomization at every step. So I hope this kind of makes sense and you appreciate why this kind of a thing is important. Yeah. So so yeah, in general, actually mixed strategies and behavioral strategies are not equivalent. But then why did we even define all this equivalence and everything if like they are actually not equivalent? So you can actually show under some assumptions. This was discussed in this week's lectures also with under Cohen's theorem, and I'll be discussing this also. That under some assumptions of the game, if there is some kind of a structure to the extensive form games, which I'll be describing the structure also, then actually mixed strategies and behavioral strategies will be equivalent. Like every mixed strategy could be simulated by a behavioral strategy and vice versa. So first of all, before like proceeding to what like the equivalence of these, let's just first discuss a definition, like what's a perfect recall. So perfect recall is so perfect recall means that a player does not forget anything. Like on a intuitive level, if a player has a perfect recall in a game, it means that the player has not forgot anything. And like, what does this mean on an intuitive level? If a player has to forget nothing, so what kind of things can a player actually forget? So a player can actually forget the actions that the player took. A player can also forget that whether he took an action at all. Like here, like these two information sets, these two nodes were in the same information set, right? So player cannot distinguish between these two nodes. So player has actually forgotten even if he took an action at all, because P1 cannot distinguish between one node at a higher level and node at a lower level. So P1 does not even remember if he took an action at all, right? And the player should not forget what he knows. So if a player does not forget anything, like you can kind of like categorize forgetfulness as something like this, that what can a player actually forget? Player can forget actions that the player took. Player can forget that whether he took an action at all. Player can also forget what he already knew. So it might be possible that player earlier knew something, but in later stages it forgot something. And like if a player has a perfect recall, then it should actually not forget anything. So player PI has a perfect recall. So this is the definition, like a PI. Like this is just an intuitive definition. Now we'll try to formalize it. So a player PI has a perfect recall if so. Like first, let's say like this kind of a definition, like the player cannot forget that he took an action at all. So if a player forgets that he took an action at all, what this means is that two nodes, if a player forgets that he took an action at all, what this actually means is two nodes which are at different levels of the game tree for that player. So here you can see like for player one, these two nodes were at different levels of the game tree, but they were in the same information set. And that's why player one forgot whether he took an action at all. So essentially, uh, and these nodes had an ancestor descendant kind of a relationship. So any ancestor descendant nodes of the same player should not lie in the same information set, because if two nodes which have an ancestor descendant relationship lie in the same information set, then actually the player cannot distinguish between these two nodes. And so like the player cannot distinguish between two levels of the game, which essentially means that the player forgot whether he took an action at all. So this cannot forget that he took an action at all can be formalized by just saying that every information set intersects every path at most once. And what does this mean? Like this is just equivalent to saying that no two ancestor descendant nodes are in the same information set. So this part one just says that the this is just a formalization of with player not taking an action at all. Yeah. So essentially, like perfect recalls, informal definition of perfect recall, like we call that a player has a perfect recall if every information set intersects every path at most once for that player. Okay. And the second point is like we still have to ensure that a player does not forget the actions he took and does not forget what he knows already. So if x prime and x double prime are in the same information set, then this means that the player cannot distinguish between x prime and x double prime, right? But suppose x is some predecessor, and similarly x hat is also x is some predecessor of x prime and x hat is predecessor of x double prime, right? Then like these two nodes x and x hat also should be in the same information set. And why is this the case? Because suppose and note that this is for any predecessors of x prime and x double prime. Like it's not just like immediate predecessors, but like for all ancestors, this should be happening. That like for all ancestors of x prime and for all ancestors of x double prime, like these x and x hats should be in the same information sets. And like why is this the case? Essentially, a high level idea is uh, like if x hat and x prime and double prime are in the same information set, player cannot distinguish between these two nodes. But suppose player was able to distinguish between x and x hat. So suppose these two were in the different information sets, x and x hat. were in different information sets, whereas x prime and x double prime are in the same information set, right? So what does this actually mean? This means that the player actually knew something, like suppose x and x hat were in different information sets, then the player could distinguish between these two branches of the game tree, right? Player could somehow distinguish between these two branches of the game tree. So player could actually knew something by which he or she could distinguish between these two branches. But in a later stage, the player has actually forgot. And player now in this x prime and x double prime, player cannot distinguish between these two branches, right? So a player knew something before, which the player does not know now. And this means that player has forgot something which he knew. And that's why like this cannot happen, that X and X hat cannot lie in different information sets. So they should lie in the same information set. But also another important thing is just ensuring X and X hat lie in the same information set is not enough. We also have to ensure that the player does not forget the actions that he took. And suppose if X was equal to X hat, then like X prime and X double prime, both of these originate from this X, which is equal to X hat. And the player cannot distinguish between these two nodes. So actually the player cannot distinguish between these two actions, between these two yellow actions. So another thing is uh, uh, like these two are in the same information sets, and the action taken at X along the path to X prime and uh, action taken at X hat along the path to X double prime should be the same. Like these two cannot be two different actions. Like if they were two different actions, then the player cannot distinguish between the actions that he or she took. Right. So a bunch of criteria which we need that yeah. So and if all of these are, if these definitions hold true, then we say that the player PI has a perfect recall. Right. So the second thing is just I'll just read it again. If x prime comma x double prime are in the same information set of pi and x is a predecessor of x prime, then there is a node x hat in the same information set as x and is a predecessor of x double prime. And the action taken at x along the path to x prime is the same as the action taken at x hat along the path to x double prime. So note that we are just defining this for predecessor, not for all ancestors, because this kind, like you can take predecessors of predecessors of predecessors, and yeah, and like you can do this for any ancestor if you just consider predecessor also. So this kind of a definition is sufficient for us. Okay. Okay, so this is a bunch of terminology. Like I don't, you don't see like what's the use of this. Like why are we defining all of this? So actually, this kind of a definition of perfect recall is useful because of Kunz theorem. So we're just coming to this. So actually, on a high level, I'll just give you the idea that if a player has a perfect recall, like if these conditions are satisfied for a player PI in the game, then you can actually say that every behavioral strategy will have an equivalent mixed strategy for the player, and every mixed strategy will have an equivalent behavioral strategy for the player. So under if a player has perfect recall, then he or she will have a equivalent mixed and behavioral strategies. Okay, so this is what essentially Cohen's theorem states. So, actually, perfect. Like, there are two sides to this. Okay, like one thing is to show that every behavioral strategy has an equivalent mixed strategy, and for this you require like some loser assumptions. So, if you just ensure that each path from root to leaf intersects one information set of pi at most once, then uh, every behavioral strategy of pi has an equivalent mixed strategy. So for ensuring that every behavioral strategy has an equivalent mixed strategy, just this assumption is okay for us. Like every information set intersecting every path at most once. If this is true, then every behavioral strategy has an equivalent mixed strategy. But for every mixed strategy to have an equivalent behavioral strategy, both of these should hold one and two. Like if PI has perfect recall, then every mixed strategy of PI, there exists an equivalent behavioral strategy. So this is the second part of the theorem. So first part of the theorem says that every behavioral strategy has an equivalent mixed strategy. And for this, the assumptions are a bit relaxed. The assumption just wants us to have like every information set intersects every path at most once. But for the second part, which says that uh, every mixed strategy, there exists an equivalent behavioral strategy, both of these should be followed. So, so yeah, and this is Cohen's theorem, and the proof for Cohen's theorem was discussed in the lectures, and maybe I'll not go into the proof, and you can just see the proof there. And like, even though like proof might seem notationally heavy, but on an intuitive level, it is like really not too difficult to see what's happening. Like you just equate the probabilities, and you just find out the probabilities of taking some actions, and everything works out. So yeah. Okay then. So I hope we are clear with the theory. Then if so, I'll just move on to discussion of questions. So I believe there are not so there are some questions, but yeah, like not a lot of questions, and just yeah, just 7 questions we have. So I guess uh, we'll be done early, but let's just see. I was hoping that some people will join the session in person also, and will have some doubts in this theory, and like I'll have to spend some doubts. I have to spend some time clearing those doubts. But yeah, apparently no one showed up. Okay, so now maybe we can move on to the questions then. So first question asks us to pick the correct options. Okay, so maybe let's just do it option by option now. So, so option A says that every pure strategy of a player is a mixed strategy of the player. So, okay. Uh, yeah, I'll just reconnect to the session in a minute, guys. I think I'm facing some. Like, there's some pop-up in my laptop, and like my screen just stopped sharing. I'll just reshare my screen in a minute. Okay, I think now I'm able to share my screen. Okay. Uh, yeah. I hope my screen is visible now. Yeah. So I guess this kind of a similar question is present in your quiz also, so I won't be discussing it explicitly since this is asked in this week's quiz also. But just to give you an idea of the theory, I just put this question in. So yeah, so like pick the correct options. Maybe I'll not discuss all the options because like it will just give away the answers for the quiz. So maybe I'll just yeah. Okay, maybe I'll just discuss option A first. So option A says that every pure strategy of a player is a mixed strategy for the player. So actually, you can see that this option is actually correct because every pure strategy can be simulated by like every pure strategy is just like a mixed strategy with the probability distribution. Like suppose there are like k strategies for a player like strategy 1, strategy 2 till strategy k, s1 till sk. Then you can think of the probability vector as being like if a pure strategy, if you have to play the pure strategy si, then like the mixed strategy vector will be just probability play si with probability 1 and all other sjs with probability 0. Correct, as playing a pure strategy si is equivalent to playing a mixed strategy having probability 1 for si and 0 for other strategies, right? And so like a pure strategy can be uh, thought of as a mixed strategy also. So option B, I'll just leave it to you guys to figure it out. Yeah. So okay, we showed that every pure strategy is a mixed strategy of the player, and it's not too difficult. Like these kinds of discussions we already had in. Okay, like yeah, maybe I'll just replace this option by. Okay, maybe I'll just leave this option that every mixed strategy of the player is a pure strategy of the player. So, I'll just leave this to you whether every pure strategy is or every mixed strategy is also a pure strategy. So I'll just give this as exercise to you guys. Similarly, so what's option C? So option C is something which we have already discussed in like we have already discussed in these notes itself, right? For this guys, that option C just says that a mixed strategy for a player is a probability distribution on the set of all of its pure strategies, right? And like as we had discussed that this is what a mixed strategy is. Like let's consider a set of all pure strategies and choose one pure strategy at random according to a probability distribution. So this is actually correct from the and why is this correct? It's correct from the definition of mixed strategy. Right. And option D again, I'll just leave it to you guys to do it yourself. So option D just asks that yeah. Otherwise, I'll just be revealing the whole answer to the quiz, and I don't want to that the quiz question, and I don't want to do that. So the set of mixed strategy Nash equilibria includes the set of pure strategy Nash equilibria. So the question just asks if like every pure strategy equilibria is imbibed in the set of mixed strategy Nash equilibria itself, right? So a hint for this is like I'll just give you a hint. I'll not write it down, but it's the hint is in one of the above options itself. The hint is in one of these three options itself. Yeah, let's leave it at that. Okay, like another interesting question has come to my mind just now, which I'll maybe just give you guys spot. So uh, uh, in single arc games, uh, An equivalent strategy, a, a mixed strategy, or maybe for every mixed strategy, there exists an equivalent behavioral strategy for all players. True or false? Okay, and similarly, let's add another question. Like in single act games, every uh, for every behavioral strategy, there exists an equivalent mixed strategy for all players. Okay, so these are the two questions. Yeah. So note that. Okay, so let's come to this question. That what are single act games first of all? So single act games are where every player is playing at most once, or you can think of like every player is playing exactly once, right? So if we are given like single act games, uh, for every mixed strategy, does there exist an equivalent behavioral strategy for all players? Like for each player, is it true that if each player is playing some mixed strategy, then I can convert that player's mixed strategy to an equivalent behavioral strategy? Is this true or false? So actually, if you see that criteria for Kunz theorem, the criteria for perfect recall, actually you'll notice something that the conditions for perfect recall can only be violated in multi-act games. Like, see, like a player cannot forget actions he took, player cannot forget that took an action at all, player cannot forget what he knows. And all of these are relevant only when player is playing for more than one turn. Like in these definitions, also like every information set intersects every path at most once. So if a player is playing only once, then information set anyways will intersect at exactly once. And similarly, the second definition also, like we are defining predecessors of x prime and x double prime, and predecessors will exist only if pi is playing more than once, right? So this definition of perfect recall, like conditions of perfect recall, can only be violated in multi-act games. Like in single-act games, they cannot be violated. So, and Kunz theorem says that if like the game every and this is true for any player, like so every player will be having perfect recall in single act games because there is nothing to recall if every player is playing only once. So all mixed strategies will have an equivalent behavioral strategies and vice versa also. So true. Uh, each player plays only once, and hence there is nothing to recall, which implies that the player has a perfect recall. And maybe in other words, uh, no condition of perfect recall can be violated in single games, right? Okay, and since player has a perfect recall because of Kunz theorem, since Every player has perfect recall. Kunz theorem holds, or maybe implies the statement is correct. So, yeah. So since every player has perfect recall, Kunz theorem implies that the above statement is correct. And like similarly for third question also, this will be true. Like okay, now like since like because of perfect recall, like every behavioral strategy will have mixed strategy, and similarly every mixed strategy will have a behavioral strategy. So true, and the sim explanation is similar to explanation similar to question two. So yeah, right. And maybe I'll just leave you guys with the food for thought. Okay, like we were discussing like okay, like we have discussed that in so this kind of a perfect recall, the concept of perfect recall and everything makes sense only in case of like multi-act games. In single act games, it will always hold true. But in multi-act games also, like we had considered some games like multi-stage games or like ladder nested multi-stage games. So uh maybe just a food for thought or like something which you guys should think for yourself, do it yourself. So does the or maybe do the conditions for Kunz theorem hold in case of ladder nested multi-act games, ladder nested multi-stage games, or was it called multi-stage or whatever? Like I hope you get the idea. Like so yeah, so so the in general multi-stage games, uh, like you can check for conditions of recall, but this ladder nested multi-stage games had a very specific structure. Like single act games have a very specific structure, and because of this, you can have perfect recall in single act games. So similarly, in these ladder nested multi-stage games, do you think uh, conditional Kuhn's theorem will hold, and hence can we always find an equivalent behavioral strategy for a mixed strategy in these games? Like the key idea behind these is like okay, like in like multi-stage in these ladder nested multi-stage games, and let's say like I also add like in feedback form, like which also had this feedback form. Like yeah, I'm just looking at the simplest kind of multi-act games, which we discussed last time. So you guys might remember the definition from last time. And in these games, like do the conditions for Kuhn's theorem hold? And a very high level idea which I would like to give for this is like how did we define these ladder nested multi-stage games or like multi-act games? Maybe I should write multi-act games. I don't. They are in stages, but yeah, just write it as multi-act games. So here we define these in form of like stages, and we said that no information should get lost in any stage. And every player plays at exactly once in each stage. So every player plays exactly once in each stage, and no information gets lost in any stage by the player. So these kind of things looks like similar to like conditional perfect recall, where a player does not forget anything. But still, I would urge you guys to look at this and just see the structure for these Ladness and multi-act games and actually see for yourself whether all the whether both the conditions for theorem hold or not. Like intuitively, it makes sense that it should hold, like because how we define these and how we define perfect recall. But just see for yourself, like whether these exist or not. And yeah. I'm not going to tell whether these exist or not, whether they hold or not. But yeah, it will be a good exercise for you guys to try. So yeah. Okay, then maybe we can move on to the fourth question. So fourth question says that consider the game where P1 is the row player and P2 is the column player and players are maximizing. So note that in this tuple, the first entries correspond to payoffs for the first player and second entries correspond to P2's payoffs. And now we have to answer the following questions. So option A says that there exists. Okay, maybe, yeah. So let's do it option by option. So this is a game and whether there exists. Okay, so these games are given in normal form and we are pretty comfortable with games in normal form by now, I hope. So I'll be doing like a lot of calculations orally. So a lot of these this week's quiz questions are based on normal form games only, like games in their normal form and the payoff. So that's why we are discussing questions of this form here also. But I'll be discussing this orally only because we have practiced enough questions for this kind of a setting. So yeah. So let's just think about this for a minute, guys. Like, uh, what all strategies will correspond to Nash equilibrium? So there exists. So option A says that there is a unique pure strategy Nash equilibrium. So let's just think, what are the pure strategy Nash equilibriums here? So let's look at this entry 1, 3. So does the row player have an incentive to switch? So row player's payoff is currently 1. If he switches, it goes to 0. So no incentive to switch. Does the column player have an incentive to switch? So column player has a payoff of 3 and players are maximizing, and if he switches, it goes to 0. So column player has no incentive to switch. So 1, 3, this is the Nash equilibrium. As you can see, like 0, 1 won't be a Nash equilibrium as row player will have an incentive to switch. 2, 0 will not be a Nash equilibrium because column player will have an incentive to switch. But this 3, 2 will also be a Nash equilibrium because row player's payoff goes from 3 to 2 on switching, so row player does not switch. Similarly, column player does not switch. So 1, 3 and 3, 2 are the two Nash equilibrium. False. As so C is the strategy of row player and A is the strategy of column player, and so this is a Nash equilibrium and D, B is also Nash equilibrium. Are two pure strategy Nash equilibrium for the type of game. So option A is incorrect. Let's move to option B then. Maybe I should just put as incorrect rather than false. Yeah. So option B says that every mixed strategy Nash equilibrium is a pure strategy Nash equilibrium. So actually, I think you guys already know this also that like uh, okay, so the option B says that every mixed strategy Nash equilibrium is a pure strategy Nash equilibrium. So is this statement correct or incorrect? So actually, what one can see is okay. Maybe I'll just uh, let you guys know or okay. Uh, okay. So the kind of thing which I wanted to get here is that like if you have two pure strategy Nash equilibrium, then their linear combination will also be a Nash equilibrium. And it's not too hard to see why, but maybe we'll just see here. So note that C comma A and D comma B are two pure strategy Nash equilibrium. So this is a Nash equilibrium and this is a Nash equilibrium. And what I mean by and what do I mean by their linear combination also being a Nash equilibrium? Uh, okay, maybe I'll just let's just skip this. Like, okay, maybe I'll not do this claim, but in general, like, okay, so we have to find out that whether every mixed strategy Nash equilibrium is a pure strategy Nash equilibrium or not. So how do we find out a mixed strategy Nash equilibrium? So for finding out a mixed strategy Nash equilibrium, usually what we do is yeah. So the key to finding a mixed strategy Nash equilibrium is like the role player. So the role player will play something such that for column player, both the columns somewhat become equivalent. So row player has to play C and D with some probabilities such that the payoff for the column players, which are 3 and 1 here and 0 and 2 here. So these payoffs actually become equal. Like column player is agnostic to whether we want to play A or whether he wants to play B. So you can see here that if row player plays like this row C, this with probability C and this row with probability D, then the payoff for column player will be 3C plus D. So this 3C plus D should be equal to payoff when column player plays like this capital B. So then this 3C plus D should be equal to maybe 2D. And this gives us that D equal to 3C. And from that you can get that, and C plus D also equals to 1. So what we actually get is that uh, like you'll get that row player plays C with probability 1 by 4 and D with probability 3 by 4. And similarly for the column player, like column player wants to play these two columns with probability such that row player is agnostic between playing these two rows. So if column player plays this with probability A and this with probability B, row player's payoff on playing C will be like A plus 2B, and this should be equal to like 3B. And from this, you can get that row player plays with probability, you can get A and B equal to half half. So actually, like what you will get is actually this statement will be correct, that the mixed strategy that P1 plays 1 by 4 comma 3 by 4 and P2 playing 1 by 2 comma 1 by 2. So this will actually be a mixed strategy Nash equilibrium. And note that like this is the not the only mixed strategy Nash equilibrium, but this is one of the mixed strategy Nash equilibrium. Like like as we said before, like making these rows agnostic or making these columns agnostic is one method of find out Nash equilibrium, but it does not always give us all the Nash equilibrium. Because like you can see that C comma A is also a perfectly valid mixed strategy Nash equilibrium. And similarly, D comma B is also a perfectly valid mixed strategy Nash equilibrium. But like this kind of a thing is also a Nash equilibrium. Incorrect, as the strategy is in option D form a mixed strategy Nash equilibrium, not not which is not a pure strategy Nash equilibrium. So yeah. So this is a mixed strategy Nash equilibrium, and this is not equivalent to like a C comma A or like something like D comma B, right? Okay. And now maybe let's move on to option C. So what does option C say? Like there is a mixed strategy Nash equilibrium, which is not a pure strategy Nash equilibrium. Yes, so this is correct. Like since like option B is incorrect, uh, this C is correct. Correct. As explained in option B, right? And what's option D? Maybe I should have had options in different orders, but let's just work with this only. So this is correct as row player and column player are agnostic between their two strategies for the given strategy. So like what do I mean this? That row player individually is agnostic between the strategy C and D. If column player is playing like half comma half, as I just said that payoffs are the same for playing C or D. If column player plays half comma half. Similarly, like column player is agnostic between playing A or B. If row player plays like probability 1/4 the row C and probability 3/4 the row D. So yeah. So note that this is like trying to make these columns and rows agnostic is one way to obtain a Nash equilibrium. And like this is not the only way, but yeah, one of the ways to maybe obtain a Nash equilibrium. So yeah. So like this does not give us all, but at least gives us one. Hence options C and D are correct. Right. Okay, then we move on to the fifth question. So maybe I'll just put this in the next question. So again, the game is such that P1 is the row player and P2 is the column player, and both are maximizing their payoffs. And now we want to find out like yeah, the Nash equilibrium in this kind of a setup. Okay, so again, one valid way here would be to make the rows as well as columns like agnostic to each other, but note that there are two columns, but there are four rows. So like if you try to like consider that all the four star, like if you play column capital A with probability small a and this with probability B, then if you try to make the payoff for all these four rows equal to each other, then you might get in trouble. So in this kind of a scenario, what one has to like this can result in overfitting, right? Like there can be multiple you want like if you are playing this with probability A, this is probability B, then the payoff on playing like for the row player payoff on playing C will be something, on playing D will be something, on playing E and F will be something. And if you equate all of these, then you have kind of four equations, but you only have two variables, so you will kind of be overfitting. So instead of that, what one can try to do is in fact just maybe take a subset of two rows. Like okay, so this is not a like this is a very high level idea which I'm providing, but this was kind of already discussed in the lectures also in some way or the other. But like if we are not trying to overfit, then what you can do is just maybe take a subset of two rows here. And so what you actually do is you are just considering a subset, like a 2x2 game out of this whole game. And you see whether, and you try to solve for this 2x2 game. And if you try to find a mismatch equilibrium for this 2x2 game by making like row players and column players agnostic to each other, agnostic to their other options and everything, then you will like obtain some some Nash equilibria for like some mixed Nash equilibria. Let's say if you take the rows C and D and columns A and B, then you will obtain a mixed Nash equilibria for this 2 × 2 game. But then uh, is this Nash equilibria actually equivalent to like whole game's Nash equilibria? Like here we are just considering the player is not playing E and F at all. But what if the player was actually playing like E or F as well? So that kind of a thing still remains, but then you will have to kind of check whether so you'll obtain like some values of like A, B, C, D, and like E and F will be paired with probability 0. And then you will have to check whether this kind of thing overall is also a Nash equilibria. Like as in, okay, like you can see that this ABCD form a Nash equilibria. This game has a Nash equilibria, but whether this Nash equilibria is a Nash equilibria for the whole game, then you will have to check. Like you will obtain some values for A and B, you'll obtain the values for C and D, and then you are saying that essentially E and F are played with probability 0, right? So E and F are played with probability 0, and C and D are played with probability non-zero probabilities, and then you have to see whether this row player will want to actually uh, change his or her strategy so that the payoff gets better or not. So something along these lines. So maybe it's a bit calculation based. So maybe I'll skip the calculations and yeah, I'll just leave this as a do it yourself exercise because I think yeah, it's more of a uh, yeah, it's more of a calculative question. But maybe we can just think about the pure strategy Nash equilibriums first. Like let's just ignore the mixed strategy Nash equilibria for now and just see whether what are the pure strategy Nash equilibriums for this. So does there exist any also? So this is let's consider this 0, 0 set strategy. So let's see if the row player has any incentive to switch. So you can see that row player has an incentive to switch from C to F. So this is not Nash equilibria. So here you can see that row player has a payoff of 3/2, so he has no incentive to switch as this is the highest in the row. But here, like column player has an incentive to switch from -3/2 to 0. So this is also not a Nash equilibria. Similarly, this 0, 0 will also not be a Nash equilibria. This minus half, half will also be not a Nash equilibria because in both of these cases, row players has an incentive to switch. Similarly, in this also, row player has an incentive to switch, so it will not be a Nash equilibria. Here also, okay, so here row player does not have any incentive to switch, but column player has an incentive to switch from minus half to 0. So yeah. So in all the cases, like every player, at least one of the players has an incentive to switch. So as can be seen, there is no uh, pure strategy Nash equilibrium in this game. Okay. And maybe what we can do is we can try options like there are some options which are already being given to us like option C says that whether this is a Nash equilibrium or not. So we can just check for this option whether this option forms a Nash equilibrium or not. And similarly for this E option, we'll just do this. And from these, maybe we can like answer the other options also. Like I don't want to calculate all the like I don't want to go into the calculations of taking all the sub matrices by myself and calculating and checking. But since we are given two options, we can just check for these two, right? So option C says that okay, so this strategy C is played with 1/4. This strategy F is played with 3/4, and this A is played by 3/4, and this is played with 1/4. Okay, so maybe I just write expected payoff for player one, which is the row player, is nothing but yeah. So for the row player, the expected payoff is something like 1/4 times like this strategy is played with a probability like this whole of the strategy occurs with a 1 by 4 times 3 by 4 strategy. So 3 by 4 times 0. So plus uh row player is still playing this with 1 by 4, but the column player is playing, let's say, the strategy B. So the column player plays this strategy with probability 1 by 4 times 3 by 2. So this is the payoff for the row player from this row, and from this last row, the payoff for the row player is something like 3 by 4 times, right? Like this is 3 by 4, and like the payoff is half with probability 3 by 4. So maybe I'll just copy this expression. So payoff is half, and yeah, and here the payoff is 0, right? So this is the layer one's payoff, and this is actually equal to like something like 1 by 4 times 3 by 2, which is nothing but 3 by 8. So this is 1 by 4 times 3 by 8, which is 3 by 32, plus 3 by 4 times 1 by 2, which is 3 by 8, and 3 by 8 plus times 3 by 4, which is like 9 by 32, which is something like 12 by 32, right? And what's the expected payoff for? Okay, maybe we can just check here for ourselves. So this is the payoff for P1, and like, yeah, and you can actually see that like between these rows like C and F, if the player one plays these two, like if player one wants to like make the column player agnostic between these two, like between these two columns by just playing C and F. So the the equations will be something like on playing A, the payoff will be like C times 0 plus F times half. So F by 2 should actually be equal to 3C by 2. And from that, you actually get that like F equals to 3C. And from that, you actually obtain that uh, F becomes something like 3 by 4, and C becomes like a 1 by 4. So that's how we obtain this kind of a thing. So we obtain this probability by considering this this game, this 2x2 game where like the only the rows C and F are chosen. And now like for these two rows, you can also see that the column player also has the property that the rows will become agnostic. So let's just plug in these, like instead of solving the equations, let's just plug in these. So if problem player plays this column with probably 3 by 4 and this with 1 by 4, then the rows C and F will become agnostic. So here the payoff will become something like 3 by 8. And here the payoff will become again like 3 by 2 times 1 by 4, which will be 3 by 8. So the rows C and F become agnostic, and the columns A and B become. So this is a solution for the game where just the rows are C and F and the columns are A and B, right? But note that this is not a full game because like in general, like D and like there can be non-zero probabilities for the rows D and E also. But why will these rows have like actually we can show that these rows will actually have zero probabilities. And why is this the case on intuitive level? Because like let's just see the payoff if the column player is playing 3 by 4 comma 1 by 4. Uh, the payoffs for C and F become equal, and the payoff is actually equal to something like 3 by 8. like between row C and F, the payoff is equal to 3 by 8. So if like payoff for these rows D and E actually is less than 3 by 8, then these rows will never be played, because like why would the player want to increase the probabilities of D or E if the payoff on playing D or E is actually less than 3 by 8? So the condition which we'll have to check is whether for this row D, if the column player is playing like 3 by 4 comma 1 by 4, whether the payoff is less than 3 by 8 or is it more than 3 by 8. So as can be seen for the row D, if 3 by 4 comma 1 by 4 is played, then this becomes a minus 1 by 8. The payoff on playing D becomes minus 1 by 8, which is clearly less than 3 by 8. And here also the payoff becomes something like minus 9 by 8. So D and E both have negative payoffs, right? So what this actually means is these two rows will indeed be played with zero probability. Like, why would the row player want to give any probability to these? So C, only the row C and F will be played. And since these rows C and F are played, their probabilities we can calculate, which was equal to 3 by 8. So note that it's a lot of like verification. Like this is more of a verification of whether it is an Nash equilibrium rather than solving. So if given this, we can verify by ourselves if this is a Nash equilibrium by just checking the payoff for D and D. Like if D and D's payoff were like, let's say, payoff for any of the rows was bigger than 3 by 8, then we would have said that, okay, maybe C and F is not a Nash equilibrium because now the player would want to maximize payoff, so it would want to increase the probabilities of D and D. And similarly, like this 3 by 4 comma 1 by 4 will still remain, right? So this is 3 by 8, which is equal to note that payoff for P1 on playing D or E if P2 plays 3 by 4 comma 1 by 4 is less than 3 by 8, and hence D comma E will be played will indeed be played with zero probability. Hence, the given strategy, the given mixed strategy is indeed a Nash equilibrium. Mixed Nash equilibrium. Okay. So I've done a lot of these things orally, but I guess the high level idea should be clear to you guys that we just check, like for the given solution, we just check for the payoffs. And we see like if the payoffs are less than what the payoffs which we have for the current strategies, then we won't actually be playing those strategies. Yeah, this is the key level idea. And like if one had to find out actually the Nash equilibrium, like I just checked for these options, but if you actually had to find out, then you have to check for like all 2 cross 2 possible matrices, and you have to check this manually. Like how many 2 cross, like how many time, like in how many ways can we choose 2 rows out of these? There will be 4 choose 2, which is 6 ways. So I did not want to go into those 6 ways and check for each of those. I just took out these options and checked whether they form a Nash equilibrium or not. So let's just check option E also, whether this forms a Nash equilibrium or not. So option E says that okay, column player plays column player plays both the columns with probability half. So both the columns are played probability half, and again we are just checking for the row C and F. So if we are checking for the row C and F, and column player is playing both of these with probability half, so payoff on playing C will actually be equal to something like a 3 by 4. Right? So payoff on playing C will be something like a 3 by 4, whereas payoff on playing F will be something like a 1 by 4. So obviously, like payoff on playing C is greater. So why would the row player want to give weightage to F? So row player would want to give more weightage to C. and hence this would not be a Nash equilibrium. If P2 plays a half comma half, payoff for P1 on playing C is equals to like 3/4, whereas payoff on playing F is equals to 1/4. Hence, uh, P1 will not play F with non-zero probability, or maybe just will not play F with non-zero probability if P2 plays half comma half. Hence, this is not a Nash equilibrium. So yeah, we just check that this is not a Nash equilibrium. Yeah. So for these two options, actually, we check that these two are Nash equilibrium and like. So option D, maybe we should also write about option D. Yeah. So option D was also about like every Nash equilibrium of the above game is a pure strategy. So we already said that no pure strategy in this game is a Nash equilibrium. So incorrect. As can be seen, there is no pure strategy Nash equilibrium in this game. Yeah. Okay. So between options A and B, so we have to find out whether there exists only one Nash equilibrium or there exists more than one Nash equilibrium. This is something you should try it for yourself. Okay, so we just checked for these two whether one of these is a Nash equilibrium. We found out that this is a Nash equilibrium. Maybe you can take some other subset of rows and check whether this works for some other subset of rows also. And can you find out Nash equilibrium in that setting? Or maybe something like that. If you can, then it's well and good, and we can indeed say that. So it's a Nash equilibrium. So yeah. Okay, so yeah. Option A, option B, maybe just try it yourself. So I believe, like, I don't remember the answer, but I believe you will obtain more than one Nash equilibrium for this. And how do you do this? You just check for maybe other rows having like non-zero probabilities and something, and you will find like, hopefully you will find some other Nash equilibrium also. Okay. So yeah, I hope 6 question is done. Now, okay, we have less time and like more questions. Maybe since we have discussed already a lot of Nash equilibrium questions, maybe I'll just remove this question. Like it's again asking about Nash equilibrium. And again, the 6 question is also about Nash equilibrium. Maybe we should this also. Yeah, and just discuss some questions about the last questions about these extensive form games, since we would like to discuss 1 or 2 questions about extensive form games, right? So the question is, so consider the following extensive form game, or maybe I should just write. Yeah, it's a dynamic game. Like you can see yourself also as a dynamic game, and in this game, initially P1 is playing L1 or R1, and in the second step also P1 is playing. So it's a multi-ag, like it's a multi-stage game. Like all the players are playing more than once. It's a multi-ag game. Basically, player one is playing more than once. And at the first stage, player one is playing L1 or R1, and correspondingly, like now P1 is playing again L1 or R1. So now the question asks us in the above game, P1 has perfect recall, true or false. So what's the definition of P1 having a perfect recall? This means that okay, like we have to check that P1 does not forget anything, or essentially the conditions which we discussed, right? That every information set intersects every path at most once. If x prime comma x double prime are the same information set and x is a predecessor of x prime, then there is a node x hat in the same information set and is a predecessor, and action taken at x is the same action taken at x hat. So something like this. So you'll actually see that since all the information sets are here singleton sets, so yeah, the second condition for Kant's theorem, anyways, like for perfect recall, anyways asks us like here you can see that like every information set intersects every path that moves one. So if all information sets are of size one, then anyways this condition holds. Similarly, like here also in second condition also, like if prime comma x double prime is the same information set of pi. If all information sets are already of size one, then this condition also like will always be satisfied because this if condition will never come out to be. So what this means is that if a game always has only singleton information sets, which exactly means that in a game with perfect information, there is always perfect recall. And this kind of makes sense also. Like in a game with perfect information, every player knows everything. And what this means is that every player remembers everything also, right? So yeah. So actually here, like P1 will have indeed perfect recall. True. So this will actually be true as the conditions for perfect recall are satisfied. Right. And now let's move on to the seventh question, the last question for the day. It's again related to perfect recall. So it's the same game which we had earlier, but this time around we have these two nodes of P1 in the same information set, right? So now maybe I'll just move the definition of perfect recall down here also so that yeah, we can just check the conditions one by one. So now we know that it's a perfect information. This is not a perfect information game, so we have to check the conditions ourselves, right? Okay. Yeah. So so the first condition for perfect recall is every information set intersects every path at most once. So does this condition hold true here? So note that these are just the payoff nodes. So we have to just consider these three nodes. So this information set intersects every path at most once, right? Similarly this. So this first condition is satisfied for perfect recall. But let's look at the second condition. Second condition says that if x prime comma x double prime are in the same information set of pi, so it can be seen that here these two nodes are actually in the same information set of pi, right? For player one. And x is a predecessor of x prime. So this node is the predecessor of the first node. And similarly, this is the node. This is also the node which is the predecessor of R1 also, right? So like x is a predecessor of x prime, so this is x. And similarly, then there is a node x hat in the same information set of x, which is a predecessor of x double prime. So here you can see that x is actually equal to x hat. Like this node is the predecessor of this node as well as this node. So this is a this node is actually equal to x and also x hat. But if it is having a perfect recall, then the action taken at x along the path to x prime. So action taken at x along the path to x prime. So this is the action L1 is the same as the action taken at x side along the path to x double prime. So action taken at x along the path to action taken at x side along path to x double prime is the action R1, whereas action taken from x to the x prime is the action L1. But what the perfect recall condition says is that these two actions should be the same. But note that L1 is actually not equal to R1. So actually, this game does not have a perfect recall. So P1 does not have. So the answer to this is false, as condition 2 of perfect recall is not satisfied here. This is because x and x hat may be okay. Like this, maybe I'll just write the hello right here. This is because actions. Yeah, okay, maybe I'll just write condition of perfect recall is condition 2 is not satisfied here. And uh, like intuitively, what you can think is like if P1 chooses L1 or R1, like it still goes to the same information set. So P1 actually does not even remember whether P1 has chosen L1 or P1 has chosen R1. Like it cannot distinguish between these two nodes, so it cannot distinguish between whether it played L1 or R1. So intuitively, it can be seen that P1 does not remember the action taken at the first turn, taken at its first turn. So it does not distinguish between L1 and R1. So okay, then I guess this is all which I had for the day, and yeah, I guess we are running out of time also. So we discussed like some theory and then some questions related to perfect recall and like Nash equilibrium, and we discussed some theory also. So yeah, I guess this is it from my side, guys. I'll just stop sharing and yeah, just like thanks for watching the session, guys, and hopefully we'll see you guys in person next week. And yeah, same timings Monday 6 to 8 p.m. So till then, goodbye everyone.